Sorry. Okay, so we're finishing this morning with a talk by Riccardo Cristoferi, who will speak on phase separation in heterogeneous modes.
Thank you for the introduction. Thanks to you and the other organizers, Laszlo, Tatiana, and Lucio for the invitation. So what I would like to talk to you about today is a line of research in collaboration with Irene, Vicky, Giovanni, Adrian, and Christina. Yes, many people involved. That started when I was at Carnegie Mellon and is still ongoing. And that it has a very clear goal. That of understand the configuration of phases at equilibrium in an heterogeneous material. So before getting there, what I would like to do is to see what happens in homogeneous material. That is a theory that is well developed, not only to set the notation, but also to single out some properties that then we are going to compare to the case of heterogeneous material to see what changes. Okay. So the physical situation that we are going to consider is that of this case of a homogeneous material, namely for all the properties we care about, everything is the same. And in this material, there are some phases. And the idea is that we want to understand the equilibrium configuration. So we assume that we are able to describe the phases by assigning to each point in the material a quantity. And this quantity can be a number or a vector, depending on the situation. So thanks to the theory developed by the Vars first and Caniglia independently after, well, they say that what we see at equilibrium, so if we let the system evolve and settle at equilibrium, can be identified as minimizers of an energy, of a function. So that's why it fits into the realm of calculus operations. We want to minimize a function. So in order to describe the function, we need to choose a lot of objects. So first of all, we need to choose an order parameter that will be related to the order of energy that we consider, will be a parameter epsilon that will be very small. We need to decide the kind of material that will have the phases that will have the determined target space of the phase. And on this target space, there will be a description of the material given by a potential W. So this potential W will incorporate all the physics that we care about. And in particular, there will be, after some transformation that we don't care about, some stable phases. There will be some points Z, I, Z, K that will describe in this space Rm, that is the space where the phase lives, the ones that are the stable ones that we expect to see in the majority of the domain of the material that we have. Then the last ingredient is a singular perturbation that is together with the potential. We care about what happens when from one phase we want to transition to another. And this, it is typically a gradient square of the phase. This comes from a Taylor expansion. This is a second order Taylor expansion. That's why there is the gradient square. And this is also the reason why people do not only consider this kind of singular perturbation, but they consider even more general, because it comes from approximation. If you want to consider more general situation, that more fine information, you need to consider more general objects. Okay. So with all of these ingredients, that's the energy that we're going to consider. You might have already seen it under a lot of different names. It gets the name of, well, Van der Waals and Caniglia, it gets the name of Morton, it gets the name of Gisborne of energy, a lot of names depending on the community. The point is that's the energy. Okay. And on this energy, the homogeneity of the material is a reflect on the fact that neither the potential, nor the Wells, nor the singular perturbation depends on the point, spatial point of the material. It's all the same. So there is no reason, because it's homogeneous, to change them. Okay. So that's the function we want to minimize. Well, and it might not come as a surprise that minimizing this function is not easy, it's difficult. So the idea is that, okay, we don't know how to really minimize it, but we can take advantage of the fact that the parameter epsilon, that is what we want to choose, one of the ingredients is very small. So the idea is to say, okay, it's very small, so we can sort of tailor expand this energy. And if we are able to study these terms in this kind of Taylor expansion, then we can get more and more information on the original energy. Of course, it all depends on what this expression means, and this expression has a very specific meaning that can be understood via gamma convergence, namely, okay, the first zero order in this expansion is that the gamma limit when you send the parameter epsilon to 0. And then what you want to do is to study minimizers. So you take the original energy, you subtract the minimum, and now you have something that is 0 at the minimizers of this F naught. And you want to understand what happens if you blow up this energy with a certain rate. Of course, choosing the rate is something that you have to do, and this will select particular minimizers. And then you keep doing this operation over and over again, and you end up with this expansion. The advantage of this is that, okay, by studying these limiting terms in this expansion, you get finer and finer information on the original energy that you assume is more complicated than these other objects. This is also a selection criteria for minimizers, because the minimizers of the original energy, this F epsilon, will be minimizers of F naught that are also minimizers of F1, that are also minimizers of F2. So you kind of refine the set of minimizers that you have. And the idea is that this is why this is also called like a selection criterion for minimizers. And not only have an expansion of the energy, you have also an expansion of the value of the minimum that is also useful for physical applications. Of course, you know, there is conservation of difficulty in mathematics, so all of this scheme is not easy to carry out because you have to identify the minimum value. You not only that, you have also to understand how minimizers look like, because you want to identify the scaling parameters. So you need to have an idea of what are the structure of minimizers and more or less how they behave from the point of view of energy, which is not easy at all. And worst of all, this can simply fail because gamma limit might not exist. And you can see this in a lot of examples. In these papers, where they say, okay, this is the strategy, but to make fail, and these are very simple examples. Luckily for us, at least up to the point where we got, it does not fail. But we got two other ones, so the other two will fail. Okay, so the idea is that, okay, we have this energy, and under some very natural assumption on the regularity of the potential and the growth at infinity, I don't want to point them out because they're not the core of the discussion. Well, basically it works in the 80s, also by people in the audience. It is, well, easy to get zero powder with the sign to zero, just eliminate the gradient term. And you also know that the minimum of this limiting function is zero, so very easy, nothing to do. And you can also get the order at which this zero energy is reached. And if you do that, so you just take this function divided by epsilon disorder, you send epsilon to 0 and you see what happens. Well, what happens is that in the limit, you get something that, well, I mean, this W vanishes in these points. You have 1 over epsilon in front of W. So if you want to have something that is finite energy in the limit, the limiting object must take values in these wells. And that's basically the situation that we have. Okay, the limiting function will just weight how much it costs to go from one well to another one. It will be an interfacial energy. And the cost is kind of explicit. So you know it is just a transition energy, one-dimensional curve space that connects two zeros. And the amount of energy that you pay is with respect not to the Euclidean metric, but with respect to this degenerate metric, because this W will vanish at the two endpoints, and it may vanish in other points along the path. So that's basically the picture that we want to present. There are more works on this, in particular, recently, under some more assumption, they got to the second order. But what I want to point out is that in this scheme, so that's the energy, there are some key features that I want to underline. So first of all, I have macroscopic phase separation. Macroscopic phase separation means that, okay, and the configuration that we had in the first order gamma limit will just take values on the mass. So your domain omega, your material will be divided in regions. On each region, we have a different value. The amount of energy that you pay to go from one region to the other is isotropic, because it just depends on the amount of surface area between the regions. And this is usually, the fact that it is isotropic is usually linked to the fact that the singular perturbation that you consider is isotropic, is a gradient square. Of course, you expect, okay, if instead of paying gradient square, pay something that is anisotropic, as you saw in previous talks, you expect this limiting energy to be anisotropic as well. And finally, the amount of energy that you pay is given by a one-dimensional profile. So these three are the key properties that I would like to underline for this kind of energy. Of course, there are more words, but this, for what I'm going to talk about today, these are the key ones. Okay. So now let's see what happens when we go to from homogeneous to heterogeneous. So heterogeneous materials can be whatever. Any material that is not homogeneous, that is okay. A very wide class. And in this, for these materials, okay, also these they undergo phase separation. So the distribution of phases is also in this case we expect to describe the phases in the same way as before by assigning a number. Well, of course, if you just consider an heterogeneous material, there is very little to say because they are too generic. So as a starting point, we're going to consider a subclass of these heterogeneous materials, a very particular one. So those are that are periodic. So we assume our material to have a periodic microstructure. So you can say, okay, this is a huge simplification. Okay, we have to start somewhere, but it's not far from something that is seen and is designed in experiments, because they kind of try to say, okay, I design my material to have some sort of periodic structures. Or there will be errors and things, but those would be taken care of if you consider models that are from deterministic to stochastics. Another story. One thing that you get when you get a periodic structure is another order parameter in a model that is the order of the microstructure, that here will be a delta. And the idea is that, okay, I have a microstructure that is in a unit cell. Here, by simplicity, is a square, but you can take any shape that will tail your space, whatever space you have. And in this microstructure that we just copy and paste, that is scaled, we consider something that is, okay, some sort of singularities because we consider material inclusions. Material inclusions means that in the microstructures, I can have discontinuities. So all my objects, in the wells and the potential, they're not just continuous, we might have jumps. So it is, and here we want to understand what happens for the distribution phases. So the functional is modified in an easy way in the sense that, okay, I said before that the homogeneity of the material is reflected in the homogeneity of the potential, the wells, and the singular perturbations. Here we just consider two of these. That is the fact that the potential and these wells, they will vary with the quantity space. We do not consider the singular perturbation to vary in space. That is a choice. And we have two reasons for doing that. Because, well, the first one is that perturbation that depends on the spatial points, but all the rest fixed has been, as we see in next slides, already considered by Brades and collaborator, and seen Brades and Chiadoppia. And that is easier than in this case, because the technical difficulties they have to face are easier than in this case. And basically, that's the reason why we decided to do that. Okay, so we have the situation where we have the previous energy modified and the periodicities here in the fact that everything, the West and the potential will be periodic with respect to the period that is determined initially by the material. And what we want to understand is, okay, what happens in this case? So, as a first step, we're going to consider wells that are fixed. So instead of considering potential and wells that move, we first consider wells that are fixed. We see what happens in that case in a couple of situations, and then we're going to consider when also the wells are moving. Okay, so as I said, okay, there were sort of previous work by C. Adragis and Pietro Piat, sort of 20 years ago, where the homogenization, so the singular perturbation, depends on the spatial point, but all the rest do not. And recently, there are other lines of investigation with similar functions by Annika, Teresa, Roberta, and Caterina, where they consider stochastic homogenization and sort of the same line of ideas, but with the Ambrosio total function, which is a function for basically cracks. Okay. So before discussing everything, let's do some heuristics. So what do we expect? Because okay, if you want to prove some gamma converter result, you need to get a guess of what is going on otherwise. So, well, here we have two parameters. So you expect three kind of regimes. So a regime where one parameter is faster than the other, a regime where they are the same order, and the regime where, okay, the other parameter is faster. So what does it mean? When delta is faster than epsilon, you know that these oscillations, they are way faster than this phase transition parameter. So you sort of expect that, okay, this W will, if you see some point epsilon, some level epsilon, delta is so small that you just see an average of what is going on. When they are at the same order, more complicated, and the other case you expect the opposite. So first you go phase separation, then you homogenize. And we'll see that in the next slide. But that will be not for the zeroth order, because the zeroth order here we just want to basically send epsilon delta to zero simultaneously. What happened in the homogeneous case is that we just basically cancel the gradient term and end up with the volume term that is W. Here we have the same, we get a volume term, bulk term, but whose integrand will depend on the regime where we are. I will not write down the specific information. The only important thing is that, okay, it's a bulk term and the minimum is zero. So, okay, that is zero. And we also get the orders. So it is the same order for homogenization first, and same order is epsilon. And it is a different order when the phase separation is first. And notice that this order epsilon over delta goes to zero in this regime. So they are all quantities that go to zero. Okay. So as I said, okay, what we have to do for the first order is that we have to subtract the minimum, which is zero, so easy, and to divide by this order. So as I said, there are these three regimes, and we expect some sort of heuristics. So there are some limiting cases. So when delta is faster than epsilon, we consider the limiting case where epsilon is fixed, and we just send delta to zero. So in that case, okay, expect, okay, to get some homogenized potential because it goes so fast that, okay, it homogenizes, it's a sort of average. And then what you get here is nothing but a modica modulo, the one that we saw before. So homogeneous material. You send epsilon to zero and you get the same function. You just change what needs to be changed. Okay, when they are the same order, that is more complicated because they interact. No? The two processes, they happen at the same scale. And you expect this to be reflected in a complicated self form. But you expect the limiting function still to be of the same nature, so still to be an interfacial energy. In the other limiting case, you expect when you send epsilon to zero first, you expect to get some sort of interfacial energy where the integrand still gets the, still remembers the heterogeneity of the material, the periodicity, and then you get an interfacial energy with a periodic potential, and you want to homogenize it. And there have been works, Caffarelli, Chambol, and I would say photos because I don't remember. Very bad memory. Where they say, okay, if G is this quantity is continuous, well, we can tell you what happens in the limit. Problem is that here we want to consider G's that are discontinuous because the structures might have discontinuities. So we don't know exactly what happens. Okay. Well, these are the extreme cases. So what happens in the intermediate regimes? Is there any reason you think why, if delta is faster than epsilon, you get something different? No. So it is expected that in all of this region, you end up with the same limiting function as the one of doing one parameter at the time. And same for the other regime. For the regime where phase separation happens first and homogenization, for all of these sort of regimes, you expect to end up with the same limiting function. This is the heuristics. But what I want to stress is that in these heuristics, what you expect is that the limiting function is an interfacial energy. And this means that you expect macroscopic phase separation. Namely, you expect your limiting energy to be defined on partitions, basically, of your domain. And in each subdomain, you are equal to one of the wells. Okay. So this is the heuristic. So what I'm going to talk about is, okay, for the first case when delta is less than epsilon, what we did in a subcase, then what we did fully for the epsilon is equal to delta regime. And then for the other regime, here remember, wells are fixed, we do not know what happens. But if we consider the case of moving wells, might seem more difficult, we are able to say something. Truth is that, okay, we are able to say something in an intermediate regime. And we still miss the other half step, but okay, half step is better than 0 steps. Okay, so 3 regimes, and we can say something about each of those. So for the regime where, okay, homogenization is first, goes first, so we need to require a bit of more, the delta is a bit faster than just epsilon. And in this case, okay, this was, we proved it. Okay, we get exactly what to expect. We get, okay, the same result as we just send delta to 0, homogenize, and then you go to the limit. And you might ask, okay, is this extra assumption really needed, or is it technical? Well, we do expect it's technical. There is no reason why we should expect something different. And the reason why this assumption is there is because in the proof we use a Poincare inequality. And it's technical. There's no reason why. What is interesting is that this, because you notice, I mean, there is no dimension, no? In these 3 halves, there is no dimension, it's in any dimension, so 3 halves, it's strange. What we observed, and I'm gonna just say something very quickly because we just have very rough back on the envelope computations, is that this regime, this delta less than epsilon over 3 halves, is really a different regime when you consider wells that are moving. In that case, you expect 3 different subregimes. So these regimes where this happens, the regime where delta is equal to epsilon to the 3 halves and the other. And in that case, the difference is that, okay, wells are moving, so you have oscillations, microscopic oscillations. And so you have to compare the energy of phase separation with the energy of oscillations. And the difference between the 2, the order is exactly this one. So while in the case of fixed wells, this doesn't happen because you do not oscillate between wells. If you oscillate, it means that you're jumping, you have an interfacial energy. If wells are moving, you want to follow them. So you kind of oscillate. And the difference between the order of energy is basically this one. But in this case, nothing. It's just taken. Okay. So what happens for the same order? What happens for the same order is that we get a limiting interfacial energy. And what at first surprises us is that this interfacial energy is anisotropic. And we were really surprised because we said, okay, we expected everything to be isotropic because, okay, the singular perturbation we considered was isotropic. So why do we start with something isotropic and end up with something that is anisotropic? Well, the reason is that we had a bad heuristics in mind. The fact is that it is quite natural that it is anisotropic because there are two things that need to be isotropic for the limiting energy to be isotropic as well. The singular perturbation, the potential. The potential is not isotropic. And you can see it very, very easily because let's suppose that you are in this situation. You have an interface and you want to pass a cube from two zeros, Zi and Zj. They're fixed. And you want to pass from one to the other. And the price you pay to go from one to the other is this energy. It's basically the original energy without any parameters. So there is no epsilon or delta. This is basically the cell force. And the fact is that if you want to do this transition along this direction, it will be different from what you get if you go to another direction. Why? Well, because the world you see is very different here from there. So here, and this is because the W depends on Z. So every time you transition, if you just copy and paste the profile, okay, the isotopic singular perturbation will be the same gradient square. It doesn't see the directions, but W sees the directions because you see a different space around you in your transition. And this is also the reason why the limiting profile that in the homogeneous case was just a one-dimensional profile cannot in general be reduced to one-dimensional profile because you are seeing your space. Okay, just in very simple cases it can be reduced, but okay. In general it cannot. Okay, so just to give you a better idea of this cell formula, basically this is the quantity that quantifies how much I pay for going to from one phase to the other one, and just a couple of words on the boundary conditions. So basically this is the cell formula. So we take direction, we take a cube with two faces of this direction. We don't care about the other rotations, completely independent of that. And we take a large cube, T cube. And T is another parameter, so we just infinize, basically we can limit this quantity. And this is something that is not strange in this sort of methods, because the idea is that, okay, if your energy that you want to minimize is convex or scalar, okay, you don't need to do that, but in this case, you need to consider larger and larger cubes. The idea is that, okay, you want to do limit, you want to do gamma limit, so you want to consider the best way to transition from one well to the other one, and you can do it in a very, very large way, asymptotically very small. And the boundary condition, what are they? Okay, you consider your cube, and you consider an idealized function that is the two wells on the lower half and upper half region. You smooth it out with your favorite modifier, and that's the boundary condition that you give. Notice that this boundary condition does not depend on T. And it's something that I wrote about in the first version of the paper, so that's why there is an erratum. But what is important, okay, there is no dependence on the modifier, because otherwise it will be a bad definition. And okay, we do not lose completely the isotropy of this object, because this quantity depends only on the direction, not on the point where you are, not on the point where you have the transition. So there is a sort of half isotropy. Okay. So this is what we are able to say for fixed wells.
So just for me to understand, with this approximation, do you have an understanding of which class of signal you can impose? So let's say
that's an extremely interesting question.
Complex,
I mean, okay, no, the limiting one, you know, that is because it's the gamma limit has to be semi-continuous, you know, that is complex.
Yeah.
So it's continuous and complex.
If I give you a convex integral, can I ask you what is the W you have to use in order to approximate that?
That's a question that I have been asking myself for years. I have no idea. I would be extremely interested to answer the question, because the idea is okay. User in application, sometimes they start from this limiting one and they say, okay, let's build an approximation. I have no idea. I know there are a couple of works. Very good people, but I don't remember, where they say, okay, for some specific classes, we are able to construct within a class of approximants, because of course you can say, okay, the gamma limit can be approximated by several objects, but okay, you choose the class of limiting object and the class of approximating objects and the kind of say, okay, you do it by this, but more than that, I don't know. Will be extremely interesting because it's okay, inverse problem, no? But a bit of more information about this limiting energy, because then you can say, okay, I have a limiting function, I want to do regularity, no? It is an isotropic, so. Is it C1, C2? No idea. They were able to say a bit more about this energy in the case where W is really a product of something depending only on X and something depending only on U, with a lot of regularity. More than that is really not known, but basically that's what to do next if you want to understand the shapes and you want to do second order. It's but okay. Yes, so that's basically what we are able to do for fixed wells. So what happens for moving wells? So now I want to use a terminology that is moving and jumping. So what does it mean, moving and jumping? Moving means that wells are not constant, so they're Lipschitz, and jumping means that they have discontinuities. So the idea is that these are two different pictures. So having a discontinuity is different from being non-constant. And we want to understand what is the effect of these two properties, maybe separately, in the limiting energy. And we're going to do that by only one asymptotic regime, whereas if you stick to the one-dimensional scalar case, there have been previous work where they investigated basically all the regimes. The reason is that, okay, well, it's not easy to do that, but it is a huge simplification where in one dimension you don't see curvature. Jump points is a point. And if you have a scalar function, not a vectorial one, you can truncate it, you can a lot of things that you can't really do in higher dimensions. So the techniques in that paper can really be used to study the multidimensional vectorial problem. So that okay. So that's the kind of function we want to investigate in the case where epsilon is faster than beta. So in the case where phase separation happens at the scale that is way thinner than the homogenization. So what we prove is that, okay, the zeroth order, I have to talk about also that, is still a Bike energy, but we change the topology. Everything before was done in the stronger one topology. Here we need weak topology because we have oscillations. We cannot do better. And the limiting energy for the zeroth order, the idea is that you want to understand, okay, in every periodicity cell, how can I approximate in the best way with respect to this energy? How can I be a vector P in the best way? So if I perturb it in a periodic way, so on average I'm P, can I lower the energy of just one cell? So that's basically the meaning of heuristic meaning of this form.
So wait, you have coercivity? Yes, you have course. I mean, what kind of coercivity do you have on your functional?
W and W is well, it grows at infinity.
So you get. I mean, you have. I guess I'm just asking if you have a uniform weak L2. It should be okay. I forgot your precise assumption. So you have coercivity in weak L2.
Yes.
Along your sequence.
Yes. Because the fact is that okay, growth at infinity basically determines the weak and P topology that you have. If you at infinity you grow have U to the Z to the P is okay.
So you assume enough on W to get that.
Yes.
Yeah. Okay.
But the fact that okay, maybe this is a good thing to underline is that okay, if you have wells that are fixed and you just move the potential, you can say okay, and this is what we said. I suppose that we have a uniform potential that is below all the potential that we consider. So basically, we reduce everything to the conversions of the standard molecular model. Here you cannot, no, because wells are moving. So if you want to consider something that is below every potential you consider, the only possibility might just be zero. And if your energy is zero, you don't have much. So basically, that's why what this weak. Okay. Okay. So okay, this is the zeroth order, and we say okay, what we want to understand the minimizers, right? So the fact is that here we can really minimize very easily and minimum 0. And how do you achieve 0? Well, you are integrating something that is non-negative, so we want to make that something is W pound 0 at all points. So how do you make it 0? And now I cheat a bit, but it's just to explain the heuristics. Well, you have a potential that vanishes in some zeros. If you want to make it 0, the only way is just to have a convex combination of that thing. W star is the convexification. So 0 in the complex envelope of the complex, convex envelope of the points. So. And then, okay, that's in a cell. So basically, you want to average it out because, okay, your real variable is x, is not the cell variable. That's the heuristics. But the thing is that, okay, these are the average microstructure that we consider. And these are huge class. And inside this class, we want to consider a subclass of those that we call geometric microstructure. So the idea is that, okay, instead of considering any kind of average, we consider average by saying, okay, I just have one set for each point x. I just consider one set on which I put 1, 0, and another set where I put another 0. And the idea is that, okay, I need to understand what is the rate of convergence. And we want to understand it within the class of geometric microstructures. Of course, you change class, you change rate, and you focus on different minimizers. So that's a choice. And the idea is that, okay, we say, how can we be on average this kind of microstructure? So we can maybe use another scale, because I can just on average oscillate among other things, some on average being Zi and Zj, but I want to do it, this is a choice again, with microstructure that are geometric. And of course, okay, I need to do it with regular functions, so I need to go from A to B in a regular way, and to the boundary to connect everything in a regular way. So the idea is that, okay, what is the basically energy of this kind of configuration, where just back on the envelope computation, where if you change variable, basically that's the energy that you have to consider. And if you say, okay, up to constant, what is the order? Where the order is, okay, the order of the bulk part, that is basically 1 or 0, depending on whether A and B are wells or not, plus the gradient term. And then you have this interfacial energy from going to one to the other, that is basically just the composition, that's the quantity. And the same if you want to go from A to B, or from whatever A, B are, and you go to the other surrounding. And the fact is that we want this energy to go to 0. So first of all, better A, B, better be West, because otherwise it's 1. And second, we want to impose, it's not really imposing because this is heuristics, some sort of the fact that all of the energy, they're kind of the same order. And you can do that with just one choice of the parameters by choosing the transition layer to be of the same order that is epsilon over delta. And you see that, okay, whatever that's the best choice, and whatever other choice you do, you will never see the energy of the bulk, so of A and B, Z and Zj, because it will be always of higher order. The only thing you see is transition energy. So, okay, that's heuristic. So we just divide our function by this quantity, and this is what we get. And the idea is that, okay, we want to recall ourselves what is the microstructure that will generate some sort of local energy. So we change topology. And the idea is to change topology is basically to rewrite the function by saying, okay, I have these small cubes. I want to change variable, see what happens that cube. So I have two variables. One variable x will tell me which cube I'm in, and then I have a local variable inside the cube, y. So up to errors at the boundary of omega with current negligible, that's basically the function. And the idea is that this function is nothing but, since we're in the regime epsilon less than delta, modica mortala. There's a modica mortala inside the cell. And this modica mortala is a moving potential, but this was already considered by Shiga in the 90s. There are moving wells, but in the scalar case has already been considered by Bushit in the 90s. They are vectorial. This is a work I did with Giovanni, but they are also jumping. And this will require some sort of better approximation in order to get the limb sum. Basically, instead of approximating a general set of finite perimeter with polyhedral, you have to consider with polyhedral that are very similar to your set in the jumping regions of the potential. Basically, that's your difference. And that's the limiting energy. So the limiting energy for this function will be something that, okay, is exactly what you expect, is an interfacial energy with what? Okay, if you are in a point, if you pass from one well to the other in a point where the W is continuous, well, it's exactly the same as before, as isotropic. If instead you jump in a point where also the potential jumps, well, then you have a bit of competition, because on one side you see some potential, on the other side you see another potential, because it's not continuous. And you want to decide how much you want to see of one potential and on the other. So basically you add another variable, this point Z naught, where you say, okay, I follow one potential up to this point and then I change potential. And you want to optimize also on that. Basically, it's okay, if this is the interfaces where how much you go up and down with the profile. Basically, that's it. But the thing is that, okay, this is just in one cell. The question is, okay, let's suppose that I have multiple cells. Do I pay energy if I go from one configuration to another? Well, so let's suppose that our domain omega, we have two microstructures A and B, and I want to jump from one to the other in this hypersurface. So basically, the only change that I have to do is in these orange cubes, and basically the energy that I pay is proportional to the number of those cubes over the number of total cubes that will vanish in the limit. So I don't pay in order to pass from one microstructure to the other. And this is a huge key point, because basically what we get is not macroscopic phase separation. So what we get in the limit is a byte term, and we see microscopic phase separation in each cell. And this is different from what we expect in the heuristics for fixed wells. So that's a huge difference. And basically, that's why I also said that this half step in that direction, because this is an intermediate regime. If you have fixed wells, this is zero. If you have moving wells, you have this intermediate regime where you see microscopic but not macroscopic phase separation. And then you ask yourself, okay, that's mathematics, but can you see? Yes, you can. Apart, or at least we think you can. We found this paper, series of papers in biology, where they see explicitly, they write, okay, that they see microscopic phase separation, but not macroscopic one. So at the usual size at which they observe things and they see macroscopic phase separation, they see just random things. If they zoom way, way, way more, they see these patterns. So they see microscopic separation, but not macroscopic. So we are trying to investigate whether what we got mathematically can be applied to describe these patterns. Okay, and just to point out what are the effects, because there was the question, okay, if I go from fixed wells to moving wells, what changes, moving and jumping? Well, what changes is that we get an intermediate regime. We get microscopic but not macroscopic phase separation because of the wells that are moving. Same because of the wells that are jumping. So it seems that the two effects are the same, but at this point, that if you could, then you want to do next door, you want to do second. So you want to understand what is the minimum of your limiting energy. And the minimum is zero if and only if the wells are continuous. So there's a difference between continuous well and moving wells and jumping wells. The reason being that, okay, if you want to minimize the limiting energy, you want to follow the wells. If they are continuous, you can do it. If they jump, you cannot do it in a continuous way because you are H1 and you want to approximate something that jumps. So you need to pay always some energy. And that's the difference between the two effects. Okay. So now, since it's lunchtime, let me just wrap up with what we talked about. So we wanted to try to understand what are the equilibrium stable configuration of phases in heterogeneous materials. And that's the modification of the energy for the isotropic homogeneous material that we consider. And we saw that if the wells are fixed, so we just move the potential, and we get a parameter that is a bit faster than just epsilon, we are able to say, okay, that what we get in the limit is the same of the one parameter after the other. If the wells are fixed and we are in the regime where both parameters are of the same order, don't need to be equal, but the same order, well, we get in the limit some anisotropic phase separation. And again, this anisotropic not because the singular perturbation, the gradient square is isotropic, but because W depends on the spatial point, so you see it. Finally, we saw that if not only the potential is moving, but also the wells are moving and jumping, so they're not continuous and they have discontinuities, then in the regime where epsilon is faster than delta, so phase separation happens faster than homogenization, we have an intermediate scale that we can see by using two-scale convergence. That is basically a convergence that remembers the microstructure. And in that case, we see microscopic, but not macroscopic phase separation. Of course, a lot is open in this direction because there are all the other regimes, what happen, more general cases, stochastics, but okay, there will be for next time. Thank you.
Thank you very much. Are there any questions or comments?
So in the case of the regime where delta is like epsilon, so when you limit to that anisotropic energy.
Yes.
So have you tried to make the parabolic, not in the meaning of the maybe really making it parabolic like the immanent approximation of the interfacial flow and trying to see if you can approximate the anisotropic interfacial flow? You know, assume that you have just two wells, like
Yes.
minus 1 and 1. In this term, now, of course, we don't know what kind of energy you can recover already in the stationary case, but for those energy, can you approximate the anisotropic interfacial flow like in this? So, I mean, if you have any intuition that can be done for the approximation of the anisotropic interfacial flow.
Any intuition? No. I'm very honest. What I know is that in the work that I said that is with Raghav, Jessica, Rustom, and Irene, they consider for the case where W is just a product of something depending on X, something depending on U, you also consider the gradient flow. But I don't know if you can go to more singular ones with that technique. That I really don't know. But I mean, this is static. The reality is dynamic. So that would be interesting also because I think there are a lot of issues with the generality of these things. So I really don't know. But okay, maybe we talk after.
Any other questions? Yes.
Since Antonio has already done the question that I wanted to do.
Oh, sorry.
I go for the second one. So you are considering gamma convergence, so you are really focusing about minimizer. What about critical point?
That's extremely difficult. I mean, already in the case of the that requires more fine techniques. I mean, if you consider, I know that the work of Professor Tragawa, where they consider the basically the sharp interface limit of this one, so perimeter plus and local term. And already in that case, you need to go to variables because you can have like folding. I know there are Babanjan that is now considering convergence of critical points of the what is the same? Sorry. But the fact is that techniques are extremely more difficult. But of course, I mean, it's the other thing to understand critical points because only minimizers are. Also, I mean, this is basically for global minimizers for gamma convergence. Okay, local isolated local minimizers. If you want to understand better the landscape of the energy.
And also, I guess that you cannot know how, maybe you don't know in the stationary configuration that the measured epsilon that is associated to the solution is converging to an integral variable, right? Because you don't have monotonicity formula.
No, it's oscillating a lot. So that degree of the
Maybe just a short cheat question. So I like dynamic problems very much, but in terms of the pictures you showed us from biology, are the biologists I think they're looking at global minimizers, local minimizers, are things changing in time?
I think what they look is some sort of, I don't know if I'm using this terminology correctly, metastable states. In the sense that you observe them for quite a while, it's okay, that's stable, but maybe if they wait 1 year, you will go to another one. I mean, they claim that it's like equilibrium, but how stable it is, not, I don't really know. What I know is that what they say is that, I mean, they sometimes see this macroscopic phase separation then disappears, depending on whatever substance they consider. We liquid were now trying to read better those papers to understand what they do and what can be done. But again, I know that okay, this is static, of course, worse is dynamic.
Peter, you had the question?
Have you thought at all about the periodic setting when potential wells are not points?
Ooh, well, no, but I don't think it will be very different because in order to do all of this, basically for the lymph, we need to consider the case where the W, well, we have not the W, but some potential F that vanish in our compact set. The reason is this, okay, how do you usually go from self-formal to one-dimensional profile? You do Fubini. So basically, if you just fix a point where you jump and you want to do Fubini, in this case, you have W that changes from point to point and changes also in this direction. Whereas you would just want to consider W at that point. So you want to do, okay, let's do some approximation argument, some continuity argument. And in order to do that, you need to prove, okay, at least the road that we chose was to prove that, okay, the solution to the heteroclinic connection, if you have a solution to that problem, the Euclidean length is uniformly bounded. And in order to do that, we pass through, okay, let's assume that, okay, we have something that is zero in a compact set, we prove estimate for that, and then we go back to that case. And so I think that, okay, if W vanishes, for instance, in curves, the one you consider or more complicated objects, okay, didn't do any computation, but I don't think will be extremely more different in the techniques. If you consider something where W is not regular, close to the US, because now we consider it's basically quadratic, I don't know. But,
And maybe Dr. Hughes can want to say something. Are you able to see if he has a question? No? Okay, if there are no other questions, thank you very much again. There's lunch and break, and there's a tradition of cake at 3 o'clock, very serious tradition.